We have seen how we can use principal component analysis to reduce the dimensionality of an object image set. Now let's take a look at how we can find the principal components. So here is the problem. We're given an image set, and we will make sure that that is a mean subtracted image set, F1 through Fm. And given this, we want to find the orthonormal bases, E1 through Ek, where E1 through Ek are the principal components that we are trying to estimate, such that we can always reconstruct one of these images. We can take one of these images and express it as a linear combination of these principal components. And so for a k-dimensional orthonormal basis, that gives you the best approximation, reconstruction of the original image using just k numbers. These are the weights right here. The pKs are the weights. And what are the pKs? Well, that you get from your forward projection. Essentially, you take an image and you find the dot product with all of the principal components, you get the pKs. So that's what makes it a linear subspace that we are trying to find, because this is a linear operation. And we want to make sure that our orthonormal bases, the principal components themselves, are orthonormal in the sense that each one is a unit vector and each one is orthogonal to the rest of them. That's given by this equation right here. So that's what we're looking for. So how do we now formulate this problem? Well, let's just look at the first principal component. What does the first principal component mean? It means that it is the direction along which the distribution of your images has maximum variance. So let's just treat our image set, all the images in the set, as a random variable f. And so what we are saying is, if you take f and you find the dot product of f with the principal component, a vector e, then we want to find the e for which the variance of this dot product is maximum. So we want to find an e that maximizes the variance of f dot e. And we know the definition of variance. The definition of variance of f dot e is the expected value. The expected e of x is the expected value of any random variable x. So it's the expected value of f dot e minus the expected value of f dot e, that whole thing squared. That's the definition of the variance that we are using for f dot e right here. And you can rewrite that. Variance of f dot e is the expected value of, we can pull e out, and that's because e is not a random variable, it's a constant in our case that we are looking for. So it's e dot f minus expected value of f, that whole thing squared. Now the expected value of f we know is 0 because we have a set of images that are mean subtracted. So the expected value of f is 0. So this then simplifies to expected value of e dot f squared. And these are vectors, as we know, and we can write this as the expected value of E transpose F transpose E. Once again, F is the random variable here, E is not. So you can pull E transpose and E out, and you get E transpose expected value of F transpose E. And this can be written as a matrix R, and this matrix is an n by n matrix, which is called the covariance matrix. So E transpose RE is the variance of F dot E. So now we want to find the E that maximizes the variance of F dot E, which means it maximizes E transpose RE with one additional constraint, that each one of these vectors must be a unit vector. So E transpose E should be equal to 1. So we can develop an objective function or a loss function, and let's define that as L. L is equal to E transpose RE minus a multiplier lambda times E transpose E minus 1. We've done this sort of used this type of a objective function before, and now we want to find the E that maximizes this objective function. We do that by finding the derivative of L with respect to E, setting it equal to 0, and that gives you R E minus lambda E equal to 0, which is the well-known eigenvalue problem. So what this is saying is that if you're able to compute this covariance matrix from a set of images, then you simply find the eigenvalues and eigenvectors of the covariance matrix, and those, the eigenvector corresponding to the largest eigenvalue is the E that we are trying to find here, as it maximizes the variance of F dot E. In fact, the eigenvector corresponding to the second largest eigenvalue is E2, which is the direction along which you have the second maximum variance in F dot E, and so on. So that's basically what we're looking for. The first principal component is the eigenvector corresponding to the maximum eigenvalue, and that applies to the second principal component, and so on. So we're able to find all the eigenvalues, all the eigenvectors that are of interest to us, and those correspond to all the principal components. So now, let's see how this is done in practice. You construct a data matrix F, which is nothing but the images F1 through Fm stacked together as columns. So that's an n by m matrix. And now you compute your covariance matrix R, which is F transpose. That gives you an n by n matrix. And you simply find the eigenvalues and eigenvectors of R, your covariance matrix. The eigenvalues are these, and the eigenvectors are these. And the eigenvectors basically give you your orthonormal basis that you're looking for. There's one little thing here that we have set aside, which we'll talk about later, which is what is a sufficient K? That is, how many of these do we need? What K should we use right here? We'll come back to this, but the basic hypothesis here, or the hope here, is that we're going to end up with a K which is much, much, much smaller than n. So you end up with an orthonormal basis. This is the basis in which we're going to represent all our images going forward. This orthonormal basis is also referred to as a linear subspace, and sometimes it's also called an eigenspace.